Polonium is a chemical element with a symbol Po and atomic number 84, discovered in 1898 by Marie Curie and Pierre Curie. A rare and highly radioactive element with no stable isotopes, polonium is chemically similar to bismuth and tellurium, and it occurs in uranium ores. Applications of polonium are few. They include heaters in space probes, antistatic devices, and sources of neutrons and alpha particles. Because of its position in the periodic table, polonium is sometimes classified as a metalloid. Other sources say that on the basis of its properties and behavior, it is unambiguously a metal. Characteristics, isotopes. Polonium has 33 known isotopes, all of which are radioactive. They have atomic masses that range from 188 to 220 U. 210 Po is the most widely available. 209 Po and 208 Po can be made through the alpha, proton, or deuteron bombardment of lead or bismuth in a cyclotron. 210 Po is an alpha emitter that has a half-life of 138.4 days. It decays directly to its stable daughter isotope, 206 Pb. A milligram of 210 Po emits about as many alpha particles per second as 5 grams of 226 Ra. A few curies of 210 Po emit a blue glow which is caused by excitation of surrounding air. About 1 in 100,000 alpha emissions causes an excitation in the nucleus which then results in the emission of a gamma ray with a maximum energy of 803 keV. Solid-state form. Polonium is a radioactive element that exists in two metallic allotropes. The alpha form is the only known example of a simple cubic crystal structure in a single atom basis, with an edge length of 335.2 picometers. The beta form is rhombohedral. The structure of polonium has been characterized by X-ray diffraction and electron diffraction. 210 Po has the ability to become airborne with ease. If a sample is heated in air to 55 degrees Celsius, 50% of it is vaporized in 45 hours to form diatomic Po2 molecules, even though the melting point of polonium is 254 degrees Celsius and its boiling point is 962 degrees Celsius. More than one hypothesis exists for how polonium does this. One suggestion is that small clusters of polonium atoms are spilled off by the alpha decay. Chemistry. The chemistry of polonium is similar to that of tellurium and bismuth. Polonium dissolves readily in dilute acids, but is only slightly soluble in alkalis. Polonium solutions are first colored in pink by the Po2+ ions, but then rapidly become yellow because alpha radiation from polonium ionizes the solvent and converts Po2+ into Po4+. This process is accompanied by bubbling and emission of heat and light by glassware due to the absorbed alpha particles. As a result, polonium solutions are volatile and will evaporate within days unless sealed. Compounds. Polonium has no common compounds, and almost all of its compounds are synthetically created. More than 50 of those are known. The most stable class of polonium compounds are polonides, which are prepared by direct reaction of two elements. Now 2Po has the antifluoride structure. The polonides of Ca, Ba, Hg, Pb and lanthanides form an NaCl lattice. BPo and CdPo have the white site and MgPo the nickel arsenide structure. Most polonides decompose upon heating to about 600 degrees Celsius, except for HgPo that decomposes at 300 degrees Celsius and the lanthanide polonides, which do not decompose but melt at temperatures above 1000 degrees Celsius. For example, PrPo melts at 1250 degrees Celsius and TmPo at 2200 degrees Celsius. PbPo is one of the very few naturally occurring polonium compounds, as polonium alpha decays to form lead. Polonium hydride, PoH, is a volatile liquid at room temperature prone to dissociation. The two oxides Po2 and Po3 are the products of oxidation of polonium. Halides of the structure POX2, POX4 and POX6 are known. They are soluble in the corresponding hydrogen halides, that is, PoClX in HCl, PoBrX in HBr and PoI4 in HI. Polonium halides are formed by direct reaction of the elements or by reduction of PoCl4 with SO2 and with PoBr4 with H2S at room temperature. Tetraholids can be obtained by reacting polonium dioxide with HCl, HBr or HI. Other polonium compounds include acetate, bromate, carbonate, citrate, chromate, cyanide, formate, hydroxide, nitrate, selenate, monosulfide, sulfate and disulfate. History, also tentatively called radium F, polonium was discovered by Marie and Pierre Curie in 1898, and was named after Marie Curie's native land of Poland. Poland at the time was under Russian, German, and Austro-Hungarian partition, and did not exist as an independent country. It was Curie's hope that naming the element after her native land would publicize its lack of independence. Polonium may be the first element named to highlight a political controversy. This element was the first one discovered by the Curies while they were investigating the cause of pitchblende radioactivity. Pitchblende, after removal of the radioactive elements uranium and thorium, was more radioactive than the uranium and thorium combined. This spurred the Curies to search for additional radioactive elements. They first separated out polonium from pitchblende in July 1898, and 5 months later, also isolated radium. In the United States, polonium was produced as part of the Manhattan Project's Dayton Project during World War II. It was a critical part of the implosion-type nuclear weapon design used in the Fat Man bomb on Nagasaki in 1945. Polonium and beryllium were the key ingredients of the Urchin detonator at the center of the bomb's spherical plutonium pit. The Urchin ignited the nuclear chain reaction at the moment of prompt criticality to ensure the bomb did not fizzle. Much of the basic physics of polonium was classified until after the war. The fact that it was used as an initiator was classified until the 1960s. The Atomic Energy Commission and the Manhattan Project funded human experiments using polonium on 5 people at the University of Rochester between 1943 and 1947. The people were administered between 9 and 22 microcuries of polonium to study its excretion. Detection. Gamma counting. By means of radiometric methods such as gamma spectroscopy, it is possible to measure the concentrations of radioisotopes and to distinguish one from another. In practice, background noise would be present and depending on the detector, the line width would be larger, which would make it harder to identify and measure the isotope. In biological medical work, it is common to use the natural 40K present in all tissues body fluids as a check of the equipment and as an internal standard. Alpha counting. The best way to test for many alpha emitters is to use alpha particle spectroscopy, as it is common to place a drop of the test solution on a metal disc which is then dried out to give a uniform coating on the disc. This is then used as the test sample. If the thickness of the layer formed on the disc is too thick, then the lines of the spectrum are broadened. This is because some of the energy of the alpha particles is lost during their movement through the layer of active material. An alternative method is to use internal liquid scintillation, where the sample is mixed with a scintillation cocktail. When the light emitted is then counted, some machines will record the amount of light energy per radioactive decay event. Due to the imperfections of the liquid scintillation method and the fact that random quenching can reduce the number of photons generated per radioactive decay, it is possible to get a broadening of the alpha spectra obtained through liquid scintillation. It is likely that these liquid scintillation spectra will be subject to a Gaussian broadening rather than the distortion exhibited when the layer of active material on a disk is too thick. A third energy dispersive method for counting alpha particles is to use a semiconductor detector. From left to right, the peaks are due to 209 Po, 210 Po, 239 Po and 241 Am. The fact that isotopes such as 239 Po and 241 Am have more than one alpha line indicates that the nucleus has the ability to be in different discrete energy levels. Occurrence and production. Polonium is a very rare element in nature because of the short half-life of all its isotopes. It is found in uranium ores at about 0.1 mg per metric ton, which is approximately 0.2% of the abundance of radium. The amounts in the Earth's crust are not harmful. Polonium has been found in tobacco smoke from tobacco leaves grown with phosphate fertilizers. Because of the small abundance, isolation of polonium from natural sources is a very tedious process. The largest batch was extracted in the first half of the 20th century by processing 37 tons of residues from radium production. It contained only 40 ASI of polonium-210. Nowadays, polonium is obtained by irradiating bismuth with high-energy neutrons or protons. Neutron capture, synthesis by reaction. In 1934, an experiment showed that when natural 209B is bombarded with neutrons, 210B is created, which then decays to 210Po via beta- decay. The final purification is done pyrochemically followed by liquid-liquid extraction techniques. Polonium may now be made in milligram amounts in this procedure, which uses high neutron fluxes found in nuclear reactors. Only about 100 grams are produced each year, practically all of it in Russia, making polonium exceedingly rare. This process can cause problems in lead-bismuth-based liquid metal-cooled nuclear reactors such as those used in the Soviet Navy's K-27. Measures must be taken in these reactors to deal with the unwanted possibility of 210Po being released from the coolant. Proton capture, synthesis by and reactions. It has been found that the longer-lived isotopes of polonium can be formed by proton bombardment of bismuth using a cyclotron. Other more neutron-rich isotopes can be formed by the irradiation of platinum with carbon nuclei. Applications: polonium-based sources of alpha particles were produced in the former Soviet Union. Such sources were applied for measuring the thickness of industrial coatings via attenuation of alpha radiation. Because of intense alpha radiation, a 1-gram sample of 210Po will spontaneously heat up to above 500 degrees Celsius, generating about 140 watts of power. Therefore, 210Po is used as an atomic heat source to power radioisotope thermoelectric generators via thermoelectric materials. For instance, 210Po heat sources were used in the Lunokhod 1 and Lunokhod 2 moon rovers to keep their internal components warm during the lunar nights, as well as the Cosmos 84 and 90 satellites. The alpha particles emitted by polonium can be converted to neutrons using beryllium oxide, at a rate of 93 neutrons per million alpha particles. Thus Po-BO mixtures or alloys are used as a neutron source, for example in a neutron trigger or initiator for nuclear weapons and for inspections of oil wells. About 1,500 sources of this type, with an individual activity of 1,850 ASI, have been used annually in the Soviet Union. Polonium was also part of brushes or more complex tools that eliminate static charges in photographic plates, textile mills, paper rolls, sheet plastics, and on substrates prior to the application of coatings. Alpha particles emitted by polonium ionize air molecules that neutralize charges on the nearby surfaces. Polonium needs to be replaced in these devices nearly every year because of its short half-life. It is also highly radioactive and therefore has been mostly replaced by less dangerous beta particle sources. Tobacco smoke from cigarettes contains a small amount of polonium isotope 210, which become deposited inside their airways and deliver radiation directly to surrounding cells. The lungs of smokers can be exposed to 4 times more polonium than those of non-smokers, and specific parts may get 100 times more radiation. One study estimated that someone smoking 1.5 packs a day receives the equivalent amount of radiation as someone having 300 chest X-rays a year. Biology and toxicity. Overview: polonium is highly dangerous and has no biological role. By mass, polonium-210 is around 250,000 times more toxic than hydrogen cyanide, compared with about 250 mg for hydrogen cyanide. The main hazard is its intense radioactivity, which makes it very difficult to handle safely. Even in microgram amounts, handling 210Po is extremely dangerous, requiring specialized equipment, adequate monitoring, and strict handling procedures to avoid any contamination. Alpha particles emitted by polonium will damage organic tissue easily if polonium is ingested, inhaled, or absorbed, although they do not penetrate the epidermis and hence are not hazardous as long as the alpha particles remain outside of the body. Wearing chemically resistant and intact gloves is a mandatory precaution to avoid transcutaneous diffusion of polonium directly through the skin. Polonium delivered in concentrated nitric acid can easily diffuse through inadequate gloves, or the acid may damage the gloves. It has been reported that some microbes can methylate polonium by the action of methylcobalamin. This is similar to the way in which mercury, selenium and tellurium are methylated in living things to create organometallic compounds. As a result, when considering the biochemistry of polonium, one should consider the possibility that polonium will follow the same biochemical pathways as selenium and tellurium. Studies investigating the metabolism of polonium-210 in rats have shown that only 0.002 to 0.009% of polonium-210 ingested is excreted as volatile polonium-210. Acute effects. The median lethal dose for acute radiation exposure is generally about 4.5 a sievert. The committed effective dose equivalent to 10 Po is 0.51 AA micron sievert per becquerel if ingested, and 2.5 AA micron sievert per becquerel if inhaled. So a fatal 4.5 a sievert dose can be caused by ingesting 8.8 MBq, about 15 nanograms, or inhaling 1.8 MBq, about 10 ng. 1 gram of 210 Po could thus in theory poison 20 million people, of whom 10 million would die. The actual toxicity of 210 Po is lower than these estimates, because radiation exposure that is spread out over several weeks is somewhat less damaging than an instantaneous dose. It has been estimated that a median lethal dose of 210 Po is 15 megbecquerels, or 0.089 micrograms, still an extremely small amount. Long-term effects. In addition to the acute effects, radiation exposure carries a long-term risk of death from cancer of 5–10% per sievert. The general population is exposed to small amounts of polonium as a radon daughter in indoor air. The isotopes 214 Po and 218 Po are thought to cause the majority of the estimated 15,000–22,000 lung cancer deaths in the U.S. every year that have been attributed to indoor radon. Tobacco smoking causes additional exposure to polonium. Regulatory exposure limits and handling. The maximum allowable body burden for ingested 210 Po is only 1.1 a kbq, which is equivalent to a particle massing only 6.8 picograms. The maximum permissible workplace concentration of airborne 210 Po is about 10 a becquerel per meter 3. The target organs for polonium in humans are the spleen and liver. As the spleen and the liver are much smaller than the rest of the body, if the polonium is concentrated in these vital organs, it is a greater threat to life than the dose which would be suffered by the whole body if it were spread evenly throughout the body, in the same way as cesium or tritium. 210 Po is widely used in industry, and readily available with little regulation or restriction. In the U.S., a tracking system run by the Nuclear Regulatory Commission was implemented in 2007 to register purchases of more than 16 curies of polonium-210. The IAEA is said to be considering tighter regulations. There is talk that it might tighten the polonium reporting requirement by a factor of 10 to 1.6 curies. As of 2013, this is still the only alpha-emitting byproduct material available, as a NRC-exempt quantity, which may be held without a radioactive material license. Polonium and its compounds must be handled in a glove box, which is further enclosed in another box, maintained at a slightly higher pressure than the glove box to prevent the radioactive materials from leaking out. Gloves made of natural rubber do not provide sufficient protection against the radiation from polonium. Surgical gloves are necessary. Neoprene gloves shield radiation from polonium better than natural rubber. Well-known poisoning cases. The murder of Alexander Litvinenko, a Russian dissident, in 2006 was announced as due to 210 Po poisoning. According to Professor Nick Priest of Middlesex University, an environmental toxicologist and radiation expert, speaking on Sky News on December 2, Litvinenko was probably the first person ever to die of the acute I plus or minus radiation effects of 210 Po. It has also been suggested that Irene Joliot-Curie was the first person to die from the radiation effects of polonium. She was accidentally exposed to polonium in 1946 when a sealed capsule of the element exploded on her laboratory bench. In 1956, she died from leukemia. According to the book The Bomb in the Basement, Several deaths in Israel during 1957–1969 were caused by 210Po. A leak was discovered at a Weizmann Institute laboratory in 1957. Traces of 210Po were found on the hands of Professor Drossady, a physicist who researched radioactive materials. Medical tests indicated no harm, but the tests did not include bone marrow. Sadie died from cancer. One of his students died of leukemia, and 2 colleagues died after a few years, both from cancer. The issue was investigated secretly, and there was never any formal admission that a connection between the leak and the deaths had existed. Abnormally high concentrations of 210Po were detected in July 2012 in clothes and personal belongings of the Palestinian leader Yasser Arafat, who died on November 11, 2004 of uncertain causes. The spokesman for the Institut de Radiophysique in Lausanne, Switzerland, where those items were analyzed, stressed that the clinical symptoms described in Arafat's medical reports were not consistent with polonium-210 and that conclusions could not be drawn as to whether the Palestinian leader was poisoned or not, and that the only way to confirm the findings would be to exhume Arafat's body to test it for polonium-210. On November 27, 2012, Arafat's body was exhumed and samples were taken for separate analysis by experts from France, Switzerland and Russia. On October 12, 2013, The Lancet published the group's finding that high levels of the element were found in Arafat's blood, urine, and in saliva stains on his clothes and toothbrush. The French tests later found some polonium but stated it was from natural environmental origin. Later Russian tests released in December 2013 found that Arafat's death was not caused by radiation. Vladimir Pierre, the head of the Russian Federal Medical and Biological Agency, stated that Arafat died of natural causes and they had no plans to conduct further tests. Treatment: it has been suggested that chelation agents such as British anti-Lewizard can be used to decontaminate humans. In one experiment, rats were given a fatal dose of 1.45 mbq/kg of 210Po. All untreated rats were dead after 44 days, but 90% of the rats treated with the chelation agent OETC remained alive after 5 months. Detection in biological specimens: polonium-210 may be quantitated in biological specimens by alpha particle spectrometry to confirm a diagnosis of poisoning in hospitalized patients or to provide evidence in a medical legal death investigation. The baseline urinary excretion of polonium-210 in healthy persons due to routine exposure to environmental sources is normally in a range of 5 to 15 mbq/day. Levels in excess of 30 mbq/day are suggestive of excessive exposure to the radionuclide. Commercial products containing polonium-210Po is manufactured in a nuclear reactor by bombarding 209B with neutrons. 100 grams are produced each year, almost all in Russia. 210Po is contained in antistatic brushes, which are used in some printing presses. Some antistatic brushes contain up to 500 microcuries of 210Po as a source of charged particles for neutralizing static electricity. In USA, the devices with no more than 500 AA micron psi of 210Po per unit can be bought in any amount under a general license, which means that a buyer need not be registered by any authorities. Tiny amounts of such radioisotopes are sometimes used in the laboratory and for teaching purposes, typically of the order of 4 to 40 a kbq, in the form of sealed sources, with the polonium deposited on a substrate or in a resin or polymer matrix, are often exempt from licensing by the NRC and similar authorities as they are not considered hazardous. Small amounts of 210Po are manufactured for sale to the public in the United States as needle sources for laboratory experimentation, and are retailed by scientific supply companies. The polonium is a layer of plating which in turn is plated with a material such as gold. This allows the alpha radiation while preventing the polonium from being released and presenting a toxic hazard. According to United Nuclear, they typically sell between 4 and 8 sources per year. Occurrence in humans in the biosphere: polonium-210 is widespread in the biosphere, including in human tissues, because of its position in the uranium-238 decay chain. Natural uranium-238 in the Earth's crust decays through a series of solid radioactive intermediates including radium-226 to the radioactive gas radon-222, some of which, during its 3.8-day half-life, diffuses into the atmosphere. There it decays through several more steps to polonium-210, much of which, during its 138-day half-life, is washed back down to the Earth's surface, thus entering the biosphere, before finally decaying to stable lead-206. As early as the 1920s, Antoine Lacassagne, using polonium provided by his colleague Marie Curie, showed that the element has a very specific pattern of uptake in rabbit tissues, with high concentrations particularly in liver, kidney and testes. More recent evidence suggests that this behavior results from polonium substituting for sulfur in sulfur-containing amino acids or related molecules and that similar patterns of distribution occur in human tissues. Polonium is indeed an element naturally present in all humans, contributing appreciably to natural background dose, with wide geographical and cultural variations, and particularly high levels in Arctic residents, for example. Tobacco. Polonium-210 in tobacco contributes to many of the cases of lung cancer worldwide. Most of this polonium is derived from lead-210 deposited on tobacco leaves from the atmosphere. The lead-210 is a product of radon-222 gas, much of which appears to originate from the decay of radium-226 from fertilizers applied to the tobacco soils. The presence of polonium in tobacco smoke has been known since the early 1960s. Some of the world's biggest tobacco firms researched ways to remove the substance to no avail over a 40-year period but never published the results. Food. Polonium is also found in the food chain, especially in seafood. See also, decay chain, polonium halo, references. Bibliography, Bagnall, K.W. The Chemistry of Polonium. Advances in Inorganic Chemistry and Radiochemistry 4. New York, Academic Press PPA 197 226 doi, 10.1016 per second 0065-2792, 08, 60268X. ISBN A0-12-023604-4. Retrieved June 14, 2012. Greenwood, Norman N. Earnshaw, Alan. Chemistry of the Elements. Butterworth Heinemann. ISBN A0080379419. External links, Chemistry and its Element podcast from the Royal Society of Chemistry's Chemistry World, Polonium at the periodic table of videos.